Hi everyone, welcome to Mash Math. Today we are going to study chapter 10 circles, theorem 10.1. The theorem says the tangent at any point of a circle is perpendicular to the radius through the point of contact. So let's see. First of all, try to understand. I have already explained to you in the introduction part what is called tangent. So tangent meaning is what? And then perpendicular you know, and radius you know, then point of contact. This also I have explained to you. So what is a point of contact and what is tangent? Tangent means I told you there is a circle is there with center, and at any one point when a line is passing through, we call it tangent. And then this is radius, so we have many radius here. So one radius here, with that radius will be touching the tangent at the same point where the tangent is passing through. At that same point, radius also is touching that point. We call it point of contact. Is it clear to you? So now what does the theorem says? That tangent at any point of the circle is perpendicular to the radius through the point of contact. So first of all, let us draw a circle, then I will explain to you. Now this is the circle with center O. Okay. So a tangent at any point of the circle. So at any point of the circle, let us take there is a tangent. Okay. At this point, we'll take a tangent. Okay. So let's name this tangent as AB. So at this point, the tangent is passing through. Okay. So this is a perpendicular to the radius through the point of contact. So this is the point of contact. So from here, let's draw a radius. Okay. So now this is the radius. So we have to prove that this is, let's name it, this is as P, this point of contact. Okay. So we have to prove that OP is perpendicular to AB. So that's what we have to prove. So let's first write down what is given to us. Whenever theorem, you have to write down what is given. So given to us is a circle. A circle with center O. That is given to us. A circle with center O and a tangent. Tangent at one point, at one point of a circle. Okay, circle with center O is given to us and a tangent at one point of the circle. So the tangent name is AB. Tangent, you can write it here AB, or a tangent at one point of the circle. That's also is okay. Okay, that is given to us. What we have to prove? What we have to prove is that OP is perpendicular to AB. So that's what we have to prove. So let's prove now. Now before that, we have to do some construction here, because how we are going to prove is, for example, if this is a place, okay, this is my home, and here is the playground is there. Now to go to playground, we can go from this way also we can go, or from this way also we can go. But if I go straight, then this becomes the shortest distance. So when it becomes shorter, when the line is perpendicular, then only we call it is shorter distance. So in geometry, there is a concept is there that when there is a line, and this on that line you take any line on this point, but a side, this is the shortest line. See, this is a line. You can take anywhere the line. You can take here line. You can take here line. So anywhere you can take line on this line. No, anywhere point you can take. So, but the shortest point will be the straight one. So if it is perpendicular, then that will be the shortest distance. Okay. So based on this concept only, this theorem we are going to do. So to prove that OP is perpendicular to AB, we have to prove that OP is the shortest distance. If you prove that OP is the shortest distance, then we can say OP is perpendicular to AB. Is it clear now? So let's first take a point. Take a point on AB outside the circle. Okay, take a point Q, you can name it. Okay, so now this is AB line is at anywhere we will take one point other than the point of contact. We'll take any other point here. Okay, I am taking here point Q and join that with O. Okay, outside the circle and join with O. Okay, now let us name here also, that is a point called R. On the circle on OQ line. Okay, on the circle, the point, okay, I'll write down properly. On the circle, the point R is on OQ. Okay, just I'm describing this. So there is a on OQ, on the circle there is another point R. Okay, so that much is enough. So now let's go to proof. Now what we can prove? So first let us write down OP and OR equal. Why? Because on this circle P also is there on the circle, R also on this circle only. So both the points become the radius of the same circle. So therefore we can write OP is equal to OR. Reason, they are radii of the same circle. Okay, so next thing we can write that OR is smaller than OQ. Okay, OR is smaller than OQ. OR is smaller than OQ because OR is part of OQ. So that means whole is greater than the part. You can say whole is greater than its part. Okay, so OQ is greater than OR. Now you see between these two, so OP is equal to OR. So instead of OR, can we write down OP? So we wrote OP and this we write as it is. Here you can write OP is equal to OR. Okay, so now you see already we have proved that OP is shorter than OQ or smaller than OQ. So OP is smaller than OQ. So if I have to take anywhere the point, here also I can take, here also I can take, here also I can take. So if I join this point all with O, even then OP will become smaller than this point because these are outside the circle. Only this P is on the point of the contact. So we have, so this becomes the shortest distance. So hence OP is the shortest side of the line AB. Okay, so OP becomes shortest side of the line AB. Therefore, OP is perpendicular to AB. Hence, proved. So this is what we have to prove. It's very small, just 3 lines only you have to remember. You see, only this much you have to remember. So there is not much difficulty about this theorem. Just understand the concept and it's very clear, this theorem. That's it. Thank you and God bless you.